A million miles from Earth, a mirror made of gold is quietly gathering light that has traveled for billions of years. Welcome to the Sleepy Lab. Tonight, we will drift through the story of how this mirror came to be, how it unfolded itself in the cold of space, and why it sees what no other telescope ever could. If this is your first visit, consider subscribing, one sleepy soul at a time. Now, let's begin. On the morning of December 25th, 2021, a rocket lifted off from a launch site near the equator, carrying the most complex observatory ever built. Inside the nose of that rocket, folded carefully like a piece of origami too precious to crease, was the James Webb Space Telescope. It rose through the atmosphere, passed beyond the thin blue line of sky, and began a quiet journey outward. Not to the moon, not to Mars, but to a place far more subtle. A place called the second Lagrange point. About 1,000,000 miles from Earth, there is a region of space where the gravitational pull of the Sun and the Earth find a kind of balance, a gentle equilibrium. A place where an object can orbit the Sun in step with our planet, never falling behind, never drifting ahead. Webb reached this point roughly a month after launch, and there it remains, even now circling that invisible anchor in the dark. At the Lagrange point, something useful happens. The Sun, the Earth, and the Moon all stay on the same side of the telescope, always behind it, always in the same direction. This means a single shield can block their light and their warmth all at once. And that shield is remarkable in its own right. 5 thin layers of a material called kapton, each one coated with aluminum, and the 2 outermost treated with silicon. Together, they stretch out to roughly the size of a tennis court. 5 membranes, thinner than a human hair, standing between the telescope and the Sun. On the sunlit side, temperatures reach over 100 degrees Celsius. But on the shaded side, where the instruments wait in silence, the temperature drops to about -233 degrees Celsius. That is cold enough to slow nearly all molecular motion, cold enough that the faintest warmth from a distant star becomes visible against the stillness. And this is the key to everything Webb does. Because Webb does not see the kind of light your eyes see. It does not collect the blues and greens and reds of the visible spectrum. Instead, it watches in infrared. Infrared light is a longer, slower wave. It sits just beyond the red end of the rainbow, in a region our eyes cannot reach. But it carries information that visible light cannot. You see, the universe is full of dust, vast clouds of it, stretching across light years, dense enough to block the glow of stars behind them. A visible light telescope like Hubble looks at these clouds and sees darkness, a wall, an ending. But infrared light passes through. It slips between the grains of dust the way a low sound passes through a closed door. And on the other side, there are stars being born, galaxies assembling themselves, entire worlds hidden from every eye that came before. This is what Webb was built to find, the things behind the curtain. And to find them, it needed a mirror, unlike any other. The primary mirror of the James Webb Space Telescope is 6.5 meters across. If you stood beside it, it would tower above you, a great golden honeycomb nearly 3 stories wide. But it could not launch in one piece. No rocket fairing was large enough to hold it fully open, so the engineers designed it to unfold. 18 hexagonal segments, each about 1.3 meters from edge to edge, fitted together like tiles in a mosaic. During launch, the mirror was folded, 2 side panels tucked inward, carrying their segments with them. And once Webb reached the darkness beyond Earth, those panels slowly swung open, one at a time, locking into place with a precision measured in billionths of a meter. Each segment is made of beryllium, a metal chosen because it is light and holds its shape even at extreme cold. Beryllium does not warp or flex when temperatures plunge. It stays true. And over each beryllium surface, a thin layer of gold was applied. Not for beauty, though it is beautiful. gold was chosen for a reason rooted in physics. Gold reflects infrared light with remarkable efficiency. Over 98% of the infrared wavelengths Webb is designed to collect are returned by that golden surface, losing almost nothing. Other metals reflect visible light well, but falter in the infrared. Gold does not falter. It catches those long, quiet waves and sends them inward toward the secondary mirror, and from there into the instruments waiting in the cold. The coating on each segment is extraordinarily thin. If you gathered all the gold from all 18 mirrors, it would form a volume roughly the size of a marble, just enough to catch the oldest light in the universe. And so there it sits, a million miles away. 18 golden petals turned toward the deep. Its sunshield holding back the warmth of our star, its mirror holding still in the cold. Waiting for photons that left their sources long before the Earth existed. Photons that have been traveling through the expanding dark for billions of years, only to end their journey here, on a thin film of gold, in the quietest place we have ever built. And from that silence, Webb begins to see. The first thing Webb showed us was a silence made visible. In July of 2022, the telescope released its first full-color image, and for a moment, the world held still. Not because the image was beautiful, though it was, but because of what it contained. It was the deepest infrared view of the universe ever captured at that time, a single exposure aimed at a tiny region of the southern sky, a patch so small you could cover it with a grain of sand held at the end of your outstretched arm. Just a grain of sand. And behind it, the universe was pouring through. The target was a galaxy cluster called SMACS 0723, a dense gathering of galaxies bound together by gravity, sitting roughly 4.6 billion light-years from Earth. The light in that image left its source around the time our own sun was just beginning to form, before the Earth had cooled, before the oceans had gathered, before any living thing had drawn breath on this world. That light was already on its way. But the cluster itself was not the discovery. It was what lay behind it. Thousands of galaxies, scattered across the frame like dust caught in a beam of light. Some were spirals, their arms faintly curling. Some were red, ancient, stretched thin by the expansion of space. Some were small, faint smudges, barely there at all. And many of them were far, far older than the cluster in the foreground. They were visible because of something called gravitational lensing. The immense mass of SMACS 0723 warps the fabric of space around it, and that curvature bends the paths of light passing nearby. Light from galaxies far behind the cluster is bent inward, focused, magnified, the way a drop of water on a page magnifies the letters beneath it. Galaxies that would otherwise be too faint, too distant, too deeply buried in the past to ever reach our instruments, were gently lifted into view by the gravity of the cluster between us and them. Some of those lensed galaxies appeared as thin arcs, their shapes stretched and distorted by the bending of space. Each arc a portrait of something impossibly far away, painted in light that had been quietly redirected across billions of years. And this was only the beginning. Within months of its first observations, Webb began finding galaxies that should not have been there, not in the sense that they defied physics, but in the sense that they defied expectation. They existed in an era so early, so close to the beginning of everything, that our models had predicted only small, dim, formless clumps of matter. The first tentative gatherings of gas, not yet organized into anything resembling a galaxy. What Webb found instead were galaxies already large, already structured, already bright, existing just 300 to 400 million years after the beginning of the universe. To understand how early that is, consider this. The universe is roughly 13.8 billion years old. 300 million years is a little over 2% of that entire span. It is like opening a book of 1,000 pages and finding a fully written chapter on page 20, the ink barely dry, the words already formed. These galaxies had no right to be so mature. They contained billions of stars. They had recognizable shapes, Some showed signs of rotation, of internal structure, of chemistry that implied generations of stars had already lived and died within them. All of this in what was supposed to be the dim, quiet dawn of cosmic history. One galaxy in particular drew attention. A faint red object cataloged as JADES, GSZ 13-0, detected as part of a deep survey program called JADES, the JWST Advanced Deep Extragalactic Survey. Its light had been stretched so severely by the expansion of space that it had shifted far into the infrared, well, beyond what any previous telescope could have seen. As far as we can tell, the light from this galaxy left its source roughly 320 million years after the beginning, making it among the most distant objects ever observed by any instrument, anywhere. It is not a large galaxy. It is compact, modest in size, but it is there. It exists in an era when the universe was still mostly dark, still mostly neutral hydrogen, still waiting for the first light to carve through the fog. And yet, there it is, a small gathering of stars, already burning, already assembled, already sending light outward into a universe that had barely begun. The discovery of galaxies like this one did something quiet but profound. It told us that our story of the early universe was incomplete. The models we had built, carefully calibrated over decades, had predicted a slower, more gradual beginning, a universe that took its time assembling its first structures, that built galaxies the way a river builds a delta, slowly, grain by grain. But Webb showed us something different. It showed us a universe that was in a hurry, a universe where gravity and gas and the first flickers of starlight worked together more efficiently than we had imagined, where the raw materials of creation fell together faster, burned brighter, organized sooner. This does not mean our models are wrong in their foundations. It means they are missing something. Some ingredient, some process, some early condition that allowed structure to emerge more quickly than expected. And finding what that missing piece might be is now one of the central questions in cosmology. Perhaps the first stars were more massive than we thought, burning through their fuel in just a few million years and seeding the surrounding gas with heavy elements that accelerated the next generation of star formation. Perhaps dark matter behaved differently in those early conditions, pulling gas together more efficiently. Perhaps there are mechanisms we have not yet considered. We do not know yet. And that is part of what makes this so quietly remarkable. Webb did not simply confirm what we believed. It opened a door into a room we thought we understood and showed us that the furniture had been rearranged. The light from JADES GSZ 13-0 traveled for over 13 billion years to reach that golden mirror. It crossed the expanding void, stretched and dimmed and nearly lost, and arrived at last, a whisper from the earliest days of everything. And Webb heard it. In the stillness of its orbit, a million miles from the nearest human hand, the telescope gathered that ancient light and held it gently, the way you might hold a letter from someone who lived long ago, not because the paper matters, but because of what it carries. And what it carries is a message, simple and astonishing in equal measure. The universe woke up earlier than we thought, and it had already begun to build. So, it had already begun to build, and not slowly, not tentatively, but with a kind of urgency that no one had predicted. The galaxies Webb found in that early darkness were not faint smudges of light struggling to exist. They were bright. They were structured. They were forming stars at a pace that rewrites what we thought we knew about the young universe. For decades, our models told a particular story. They said that after the first atoms cooled and the first clouds of hydrogen drifted together, star formation would have been a gradual process, a slow gathering, a patient accumulation of mass over hundreds of millions of years before anything resembling a galaxy could take shape. But Webb showed us something different. The galaxies it found, just a few 100 million years after the beginning, were already producing stars with remarkable efficiency, far more efficiently than our models allowed, as though the universe, in its infancy, had skipped several steps in the process we thought it had to follow. This was not a small discrepancy. It was a fundamental surprise. And there was something else, something perhaps even more quietly startling. When astronomers studied the light from these ancient galaxies, they found chemical signatures that should not have been there. Not yet, not so soon. They found oxygen. Now, oxygen is not a simple element. It is not something that existed at the beginning. In the first minutes after everything began, the universe produced only the lightest elements: hydrogen, helium, and trace amounts of lithium. That was all. The periodic table, in those earliest moments, was almost empty. Oxygen comes later. It is forged deep inside the cores of massive stars, where temperatures reach millions of degrees and atoms are pressed together under unimaginable force. And it is released only when those stars die, when they swell and shed their outer layers, or collapse and explode, scattering their contents into the surrounding void. So when Webb detected oxygen in galaxies that existed just a few 100 million years after the beginning, it meant something profound. It meant that stars had already been born in that darkness, had already burned through their fuel, had already died, and had already returned their elements to the gas from which new stars would form. Entire generations of stars had lived and perished before these galaxies were even seen. The universe was not just building early, it was recycling early. It was already engaged in the ancient cycle of stellar life and death that continues to this day. The same cycle that eventually produced the carbon in your bones and the iron in your blood. All of it, already underway, in what we once considered the empty dawn of time. And we know all of this because of the instruments Webb carries. 3 of them, in particular, work together to read the universe in ways no telescope has done before. The first is called NIRCam, the Near-Infrared Camera. It is Webb's primary eye, the instrument responsible for capturing the images that have already changed our understanding of the cosmos. NIRCam sees in near-infrared light wavelengths just beyond what human eyes can detect, and it is tuned specifically to capture the faint glow of the earliest stars and galaxies, light that has been stretched by the expansion of the universe from its original visible wavelengths into the infrared. Every deep field image Webb has produced, every glimpse of a galaxy from the first few 100 million years, passed through NIRCam first. It is the instrument that caught the light of GEADS, GSZ 13-0, the instrument that revealed those unexpectedly mature galaxies in the young universe, the quiet collector of ancient photons that had traveled for over 13 billion years. But seeing is only part of understanding. To know what those galaxies are made of, to detect the oxygen, the hydrogen, the chemical fingerprints of stellar life and death, Webb needs another instrument. This one is called NIRSpec, the Near-Infrared Spectrograph. Where NIRCam takes pictures, NIRSpec reads the light itself. It splits the incoming glow of distant objects into its component wavelengths, the way a prism separates white light into a rainbow. And in that spread of color, each element leaves its own unique mark, a pattern of absorption and emission that tells astronomers exactly what is present, and in what abundance. But NIRSpec does something else that is quietly extraordinary. It can observe up to 100 objects at the same time. It does this through a device called a micro-shutter array, a grid of about 250, 000 tiny configurable doors, each one capable of being opened or closed independently. Each of these shutters is roughly the width of a human hair. When astronomers want to study a particular field of galaxies, they can open just the shutters that align with their targets and close all the others, blocking out unwanted light, isolating each faint source with exquisite precision. It is like having 250,000 tiny windows and choosing exactly which ones to open, letting in only the light you need, one hair's width at a time. This is how Webb reads the chemistry of the distant universe, not one galaxy at a time, but dozens at once, patiently collecting the spectral fingerprints of objects that existed billions of years before the Earth was formed. And then there is the third instrument, the one that operates in the deepest cold. It is called MIRI, the Mid-Infrared Instrument. MIRI sees in longer wavelengths than NIRCam or NIRSpec, wavelengths that reveal cooler objects, older dust, and the faintest thermal signatures of distant worlds. But to detect such subtle light, MIRI itself must be extraordinarily cold, because any warmth in the instrument would create its own infrared glow and drown out the signals it is trying to capture. So MIRI is chilled to a temperature of minus 266 degrees Celsius. That is just 7 degrees above absolute zero, the lowest temperature that physics allows, the point at which all molecular motion nearly ceases. The rest of Webb's instruments are kept cold by the Sunshield alone, passively cooled in the shadow of that tennis court-sized barrier. But for MIRI, passive cooling is not enough. It requires its own dedicated cryocooler, an active refrigeration system that pushes the instrument down to those final, extraordinary degrees. 7 degrees from the coldest anything can ever be. And in that deep, deep stillness, MIRI listens. It listens for the faint thermal whisper of dust grains in distant nebulae, for the glow of molecules in the atmospheres of worlds orbiting other stars, for the dim light of objects so cool and so far away that no other instrument could detect them. 3 instruments working together in the silence of deep space. One to see, one to read, and one to listen in the coldest dark. Each of them 1,000,000 miles from the nearest human hand, gathering light that left its source long before anyone was here to wonder about it. And night after night, orbit after orbit, they continue their quiet work, turning photons into knowledge, turning ancient light into new understanding. There is no hurry. The light has already waited billions of years. A few more hours of patient collecting will not matter. And so the instruments hold their gaze, steady and still, while the universe slowly tells its story, one wavelength at a time. But there is one more thing these instruments need before any of that quiet work can begin. Something so fundamental it is easy to overlook. They need to know exactly where to look, and not roughly, not approximately, but with a precision that borders on the impossible. This is the task of Webb's Fine Guidance Sensor, a small, dedicated instrument whose only purpose is to find a star and hold it perfectly still in the telescope's field of view. It locks on to what is called a guide star, a single point of light chosen from a catalog of hundreds of millions, and it tracks that star with an accuracy of about 1/millionth of a degree. 1/millionth of a degree. To put that another way, if you pointed a laser from New York towards San Francisco, the Fine Guidance Sensor could hold that beam steady enough to land on a single coin, without drifting, without wavering, for hours at a time. And it does this while the telescope is orbiting the sun at thousands of kilometers per hour, while the instruments are collecting photons that may have traveled for billions of years. The slightest tremor, the smallest drift, would smear those ancient photons into noise, would turn a galaxy into a blur, a spectrum into nothing. So the Fine Guidance Sensor holds. It holds with a patience and a stillness that no human hand could ever achieve. 60 times per second, it checks its guide star. 60 times per second, it whispers tiny corrections to the telescope's reaction wheels, keeping everything aligned, everything steady, everything still. And it is this stillness, this extraordinary, mechanical calm, that makes everything else possible. Because in 2022, Webb turned that perfect gaze towards something no telescope had ever truly seen before. Not a galaxy, not a nebula, but the air of another world. The planet was called WASP 39b, a gas giant, larger than Jupiter, orbiting a star roughly 700 light-years away. It is a hot world, tidally locked, with one face always turned toward its sun, its atmosphere swollen and superheated to over 800 degrees Celsius. Not a place anyone would call home, but a place where something remarkable was about to be revealed. As WASP 39b passed in front of its star, a tiny fraction of that starlight filtered through the planet's atmosphere before continuing on toward Webb. And in that sliver of filtered light, in that faint, altered glow. The telescope's spectrographs found something no instrument had ever found before in the atmosphere of a world beyond our solar system. Carbon dioxide. A simple molecule. One carbon atom bonded to two oxygen atoms. Something you exhale with every breath. Something that dissolves in oceans and feeds the growth of forests. And there it was, unmistakable, in the atmosphere of a planet 700 light-years from here. This was the first direct detection of carbon dioxide in any exoplanet atmosphere. The first time that particular molecular fingerprint had been read in starlight filtered through alien skies. But Webb was not finished with WASP-39b, not nearly. The same observations revealed water vapor drifting through the planet's upper atmosphere. Sodium and potassium, their spectral lines sharp and clear. And then, something no one had predicted. Sulfur dioxide. This was unexpected, because sulfur dioxide is not a molecule that simply exists in a hot atmosphere. It is a molecule that is produced when ultraviolet light from the host star strikes other sulfur-bearing compounds in the upper atmosphere and breaks them apart, and the fragments recombine into something new. This is photochemistry, chemistry driven by light. The same kind of process that builds and destroys ozone in Earth's own atmosphere. The same kind of process that colors the clouds of Jupiter and paints the hazes of Titan. And detecting it on WASP-39b meant something profound. It meant that Webb could do more than simply read the ingredients of a distant atmosphere. It could detect the processes, the active, ongoing chemistry happening in real time on a world no human eye will ever see directly. Not just what is there, but what is happening there. A planet 700 light-years away, doing chemistry in its sky, and a gold mirror 1,000,000 miles from Earth, quietly reading the evidence. This was the moment the study of exoplanet atmospheres changed. It was no longer a matter of detecting a molecule here or there. It became possible to understand atmospheres as living, dynamic systems, shaped by starlight, by temperature, by composition, each one a world with its own weather, its own chemistry, its own story written in wavelengths of light. And once that door was open, Webb turned its attention to a place much closer to home and far more tantalizing. 40 light-years away, which in cosmic terms is almost next door, there is a small, cool, reddish star. It is called TRAPPIST-1, and it is not much larger than Jupiter, though it is a true star, faintly burning hydrogen in its core. Around this dim red sun, 7 planets orbit, 7 worlds, each roughly the size of Earth, all of them tucked in close to their star, their years measured in days rather than months. 7 rocky worlds around, 1 quiet star, several of them orbiting within what astronomers call the habitable zone, the region where temperatures might, just might, allow liquid water to exist on a surface. No one knows yet whether any of these worlds hold water, or air, or anything at all beyond bare rock and silence. But the possibility is there, quiet and patient, waiting to be tested. And Webb is the instrument that can begin to test it. One by one, as each TRAPPIST-1 planet crosses the face of its star, Webb watches. It watches the starlight dim by a tiny fraction, and it searches that dimming for the faintest signatures of an atmosphere. The work is painstaking. The signals are extraordinarily small. Each transit lasts only a short while, and the light of the star is already faint. It may take dozens of transits, carefully stacked and combined, before a clear answer emerges. But the telescope is patient. It has fuel for perhaps 20 years, and the TRAPPIST-1 planets orbit so quickly that transits come often. And so Webb watches night after night in the silence of its orbit, gathering a few more photons each time, building up a picture so faint it is almost not there at all. Somewhere in that thin, filtered light, there may be the signature of an atmosphere, or there may be nothing, just the clean, unaltered glow of a bare world passing in front of its star. Either answer matters. Either answer changes what we understand about how common worlds like ours might be. And the telescope does not mind which answer it finds. It simply looks, with that perfect, steady gaze, 1/1,000,000th of a degree from drifting, and it waits for the light to speak. And the light did speak, quietly, in the case of TRAPPIST-1b. The innermost world, the one closest to that dim red star, returned an answer that was, in its own way, profound. Its thermal glow, measured carefully across several passes, suggested something stark. TRAPPIST-1b likely holds no significant atmosphere, no blanket of gas clinging to its surface, no veil of molecules softening the boundary between rock and space. Just a bare world, turning slowly in the ruddy light of its star, its dayside warmth radiating cleanly outward, unfiltered, untrapped. It is not the answer many had hoped for, but it is an answer, and it is real, and it was earned photon by photon across the silence of deep space. This is how the work unfolds, not in sudden revelations, but in the slow, careful accumulation of evidence, one transit at a time, one thin sliver of starlight at a time. And the method itself is quietly beautiful. When a planet crosses in front of its star, as seen from Webb's vantage point, a small fraction of the star's light passes through the outermost shell of that planet's atmosphere. If an atmosphere exists at all, the light filters through whatever gases are there, and those gases leave their mark. Each kind of molecule absorbs certain wavelengths of light and lets others pass. Carbon dioxide takes its share. Water vapor takes a different share. Methane, ammonia, oxygen. Each one removes a slightly different set of colors from the starlight. What remains, when the planet has finished its crossing, is a spectrum, a record of which wavelengths were dimmed and which were not. And in that record, like a fingerprint pressed into the light itself, is the composition of a world's sky. This technique is called transmission spectroscopy, and it is one of the most delicate measurements in all of astronomy. The atmosphere of a small planet is vanishingly thin compared to the blazing disk of its star. The signal it leaves is almost impossibly faint, a change of perhaps a few tens of parts per million in the brightness of the starlight, like trying to notice a single grain of sand removed from a vast, sunlit beach. And yet Webb can see it, because its mirror is large, and its instruments are cold, and its position in space is steady, and because it was built over 25 years by patient hands for exactly this kind of work. Webb has already turned this technique towards smaller worlds, rockier worlds, worlds more like our own. It is no longer limited to the bloated gas giants that were the easiest targets for earlier telescopes. Now it reaches toward planets where the atmosphere, if it exists, may be thin and close to the surface, where the gases present might hint at geology or chemistry or something more. The goal, still distant, but no longer impossible, is to characterize the atmosphere of a world that might be habitable, defined in the faint, filtered light of a distant transit, the chemical signatures that suggest liquid water could persist on a surface, or that some process is cycling gases in a way that only life, as far as we know, can sustain. That goal has not been reached, not yet, but the path toward it is now open, and Webb is walking it, one careful observation at a time. And while the telescope peers at the atmospheres of distant worlds, it also turns its gaze toward places where new worlds are still being born. In the southern sky, there is a region called the Carina Nebula, a vast cloud of gas and dust stretching across hundreds of light years. It has been observed before by Hubble, by ground-based telescopes, by instruments sensitive to radio waves and X-rays. But when Webb looked at it in infrared light, the view changed entirely. The dust that had hidden so much from visible light telescopes became, for Webb, something closer to a thin curtain, and behind that curtain, and within it, were hundreds of young stars that no one had ever seen before. They were embedded deep in the pillars and ridges of dense gas, tucked inside the dark folds of the nebula like embers buried in ash. Some of them glowed faintly in the infrared, their light just barely escaping the cocoons of material surrounding them. Others announced themselves through the jets of gas they were casting outward, narrow streams of superheated matter shooting into the cloud, carving bright trails through the dust. These were not mature stars. Not yet. Many of them were protostars, objects still in the process of becoming, still drawing material inward from the cloud around them, still growing, slowly, grain by grain, and wisp by wisp. They had not yet reached the threshold where hydrogen atoms in their cores would begin to fuse into helium, the moment that marks the true birth of a star. They were still gathering themselves, still collapsing under their own gravity, still wrapped in thick envelopes of infalling gas that hid them from every telescope that could not see in infrared. Some of these protostars are only a few 100,000 years old, which sounds ancient by any human measure, but in the life of a star is barely a first breath. Our own sun has been burning for 4.5 billion years. These young objects have not yet begun. And around some of them, Webb could see the faint, flattened disks of material that will one day become planets, rings of dust and gas slowly settling into the orbital plane, the earliest stage of a process that, given enough time, produces worlds. It is a strange and quiet thing to witness, the birth of stars and the seeds of planets, seen not as they are now, but as they were when the light left them, thousands of years ago in some cases, longer in others. The nebula is roughly 600 light years away. So the light Webb collected had been traveling since before the earliest Egyptian pyramids were built, carrying within it the image of stars that had not yet learned to shine. And Webb revealed all of this simply by looking at what had always been there, hidden behind dust that visible light could not cross. The stars were not new. They had been forming in those pillars for millennia, but they were new to us because we had never before had an eye sensitive enough and cold enough and far enough from the warmth of Earth to see them. This is one of the quiet revelations of the Webb telescope. Not that the universe contains surprises, but that so many of its most fundamental processes were happening just beyond the edge of what we could detect. Star formation, planet formation, the slow chemical enrichment of gas clouds with heavier and heavier elements. All of it was there, all along, waiting for an instrument precise enough to notice. And now that instrument exists, turning gently at its distant orbit, its gold mirror catching the ancient infrared glow of Nurseries, where new suns are still learning to burn. Among all the places Webb has turned its gaze, few have offered as much quiet revelation as the regions where stars are born. These stellar nurseries are vast, stretching across light years of cold gas and dust, and for most of the history of astronomy, their interiors remained hidden, because the very dust that feeds the formation of new stars also blocks the visible light that might reveal them. It is a gentle irony. The process of creation conceals itself behind the materials it requires. But infrared light behaves differently. It has longer wavelengths than visible light, and those longer waves can slip through the tiny gaps between dust grains the way ocean swells pass through the gaps between rocks in a harbor wall. What visible light cannot cross, infrared light moves through with something close to ease. And this is precisely what Webb was built to see. Its instruments collect infrared light with a sensitivity no previous telescope could approach, and when that light is gathered and translated into images, the dusty outer layers of star-forming regions become something closer to thin curtains than solid walls. The internal structure appears, the knots of denser gas, the threads of material spiraling inward, the small, bright points where new stars are quietly gathering themselves together. It is not that Webb adds anything to these regions. It simply removes the barrier that stood between us and what was already happening inside. One of the most celebrated places Webb has looked is a structure you may have seen before, even if you did not know its name. The Pillars of Creation. They are towering columns of gas and dust within the Eagle Nebula, rising like fingers reaching upward into a glowing field of light. In 1995, the Hubble Space Telescope captured an image of them that became one of the most recognized photographs in the history of science. Those tall, dark shapes against a greenish background, dense and sculptural, and strangely beautiful. That image showed the pillars in visible light, and it was remarkable for its time. But it could only show the surfaces of those columns, the outer layers where starlight illuminated the edges of the dust. What lay inside remained a mystery, like looking at the walls of a building and trying to guess the shape of the rooms within. Webb returned to the pillars nearly 3 decades later, and it saw them in 2 different kinds of infrared light. In near-infrared, the transformation was immediate. The dense dust became translucent, and the columns, which had appeared so solid and opaque in Hubble's image, now glowed with the light of hundreds of stars embedded within them. Stars that had never been seen before, not because they were not there, but because their light had been absorbed by the dust surrounding them before it could reach us. The pillars were not empty monuments. They were nurseries, filled with young stars in various stages of formation. And then Webb looked again, this time in mid-infrared light, and the view changed once more. In mid-infrared, the dust itself becomes semi-transparent in a different way. The bright young stars fade from view because mid-infrared wavelengths respond more to the cool dust than to the hot surfaces of stars, and what appeared were the pillars themselves, rendered as faint, ghostly silhouettes, pale blue-gray shapes drifting against a darker background, like columns of smoke seen through a window on a winter morning. It was the same structure, the same place in the sky, but revealed in an entirely different character. The solid, dramatic towers of Hubble's image had become something almost weightless, translucent, quiet. And within those ghostly shapes, Webb found something remarkable. Protostars, only a few 100,000 years old. In cosmic terms, a few 100,000 years is almost nothing. Our own sun has been burning for about 4.5 billion years. These protostars were newborns by comparison, still wrapped in thick envelopes of gas that was actively falling inward, drawn by gravity toward the growing core at the center. They had not yet begun stable hydrogen fusion. They were not yet true stars in the way our sun is a star. They were still becoming, still gathering mass, still pulling their birth material around themselves like a blanket. And Webb could see them, could distinguish them from the surrounding gas, could begin to measure their properties because its instruments were sensitive enough to detect the faint infrared warmth of objects barely beginning to glow. This is what it means to see the internal structure of a stellar nursery, not just to know that stars form inside clouds of gas, which astronomers have understood for a long time, but to watch the process in detail, to see the individual points of light where gravity is winning its slow contest with pressure, where matter is condensing, heating, and beginning the long journey toward becoming a sun. But Webb does not only reveal where stars are born, it also reveals where they die, and how their deaths shape the space around them in ways far more complex than anyone had fully understood. The Southern Ring Nebula is a shell of glowing gas roughly half a light-year across, expanding slowly outward from a dying star at its center. In visible light, it appears as a bright, roughly circular ring, colorful and symmetrical, the kind of object astronomers call a planetary nebula, though it has nothing to do with planets. The name is an old one, from a time when these round, glowing shapes were mistaken for distant worlds. Hubble had observed the Southern Ring Nebula before, and its images showed the bright outer shell and the faint central star responsible for it. But when Webb turned its infrared instruments toward the same object, it uncovered something no previous telescope had been able to see. The structure of the nebula was not the result of a single, smooth expulsion of gas. Instead, Webb revealed that the dying star at the center had sculpted the surrounding material through multiple ejection episodes, separate events, spaced over thousands of years, each one sending a shell or stream of gas outward at a different speed and in a slightly different direction. The result was a nebula far more complex than it appeared in visible light. Layers within layers, arcs and filaments that crossed and overlapped, each one a record of a different moment in the star's long, slow death. And there was more. The patterns in the gas suggested that the central star was not alone. that at least one companion star had influenced the shape of the ejections, tugging gravitationally on the outflowing material, redirecting it, creating asymmetries and spirals that a single star could not have produced on its own. What had looked like a simple, beautiful ring was, in truth, a deeply layered history. Thousands of years of stellar death, written in gas and dust, shaped by the gravitational conversation between two stars bound together in their final years. Webb did not just take a prettier picture of the Southern Ring Nebula, it changed what the nebula meant. It revealed that the process of stellar death is not a single event, but a long, episodic unfolding, and that the shapes we see in the sky are not decorations but records, archives of processes that played out over millennia, preserved in the slow expansion of gas that will never return to the star that released it. And so the telescope continues its work, turning from nurseries to graveyards, and finding, in both, a complexity that was always there, encoded in infrared light, waiting. Now the telescope turned its gaze towards something different, not a single star, not a nebula, but a gathering, a small group of galaxies known as Stephan's Quintet, 5 galaxies bound together in a slow, ancient dance, about 290 million light-years from Earth. Webb captured them in a single mosaic image containing over 150 million pixels, the largest image the telescope had produced at that time, a portrait so detailed that it held within it not just the galaxies themselves, but the spaces between them, the bridges of gas and dust that connect them, the scars of their interactions stretching across hundreds of thousands of light-years. And within that portrait, something violent was unfolding. One of the galaxies was falling into the group, plunging through the shared gas at roughly 800 kilometers per second, and where its material met the material already there, a massive shockwave had formed, a wall of superheated gas larger than our entire Milky Way, rippling outward through the intergalactic medium. 800 kilometers per second, that is fast enough to cross the entire width of the Earth in less than a minute. And this was not a small object moving at that speed. It was an entire galaxy, with all its stars and gas and dust, driving into the collective body of the group like a stone dropped into still water. The shockwave glowed in infrared. Webb could see it clearly, could trace its structure, could measure the temperatures within it, could watch, in a single frozen moment, the physics of a collision that has been unfolding for millions of years and will continue for millions more. But the shockwave was not the only story. Where the galaxies had passed close to one another in earlier encounters, long streamers of gas and stars had been pulled outward by gravitational tides. These are called tidal tails, ribbons of material drawn from the bodies of galaxies by the gravitational pull of their neighbors, stretched thin across the void. And within those tidal tails, Webb found something quietly remarkable: individual clumps of new star formation, small, bright knots where the displaced gas had gathered enough density to collapse under its own gravity and begin forming stars. Stars born not within a galaxy, but between galaxies, in the wreckage of a collision, in material that had been torn from its parent and flung into open space. This is one of the ways the universe renews itself. Destruction and creation are not opposites here. They are the same process, viewed from different angles. A galaxy is disrupted, its gas is scattered, and from that scattering, new stars are born in places where no stars existed before. Webb showed this with a clarity that had not been possible before. Each clump of star formation could be individually resolved, its brightness measured, its age estimated. The telescope was not just seeing that collisions triggered new generations of stars, it was showing how, mapping the precise locations where gravity gathered the scattered material back together and began the process again. Stephan's Quintet had been observed many times before by many telescopes, but Webb revealed it as something more than a beautiful grouping. It became a laboratory, a place where the mechanics of galactic interaction could be studied in detail, where the relationship between violence and creation could be read directly in the light. And then the telescope looked closer to home, not at galaxies, but at individual young stars. Stars still surrounded by the disks of gas and dust from which planets are born. These are called protoplanetary disks, flat, rotating structures that encircle newly formed stars like rings of debris. And within them, over millions of years, dust grains collide and stick together, growing slowly from microscopic particles into pebbles, into boulders, into the cores of worlds. Webb observed these disks around young stars and found something that models had predicted, but that had never been seen with such precision: gaps and rings within the disks, concentric structures where material had been cleared away or concentrated. These gaps are significant. They are the signatures of planets in the process of forming. A young planet, still growing, sweeps its orbital path clean of dust and gas, carving a visible lane in the disk around its parent star. The rings that remain between the gaps are the reservoirs of material not yet claimed by any forming world. Webb could see these structures, could measure their widths and distances from the central star, could begin to infer the masses and positions of planets that are still too young and too embedded in dust to be seen directly. This is not a photograph of a finished solar system. It is a photograph of a solar system being built, caught in the act of assembling itself from the raw materials left over after the star ignited. And within some of these disks, Webb found something even more specific. In the inner regions, close to the young star where temperatures are warm enough for liquid water to someday exist on a rocky surface, the telescope detected water vapor. Water, already present in the zone where rocky planets like Earth might eventually coalesce. This does not mean that an Earth-like world is forming in any particular disk, but it means that the ingredient most essential to life as we understand it is available, right there, in the region where it would need to be, not delivered later by comets or asteroids, but present from the very beginning of the planet-building process. The water is there before the planet is, waiting to be incorporated into whatever world eventually takes shape. And there was more still. Webb's spectrographs found complex organic molecules in the disks around very young stars. Among them, polycyclic aromatic hydrocarbons, large carbon-based molecules made of multiple interlocking rings of carbon and hydrogen atoms. These are not simple compounds. They are the kinds of molecules that, in the right conditions, can serve as building blocks for even more complex chemistry. The kind of chemistry that, given enough time and the right environment, edges toward the molecular foundations of biology. Webb found them not in one disk, but in several, suggesting that their presence is not unusual, that the raw materials for complex chemistry are a common feature of planet-forming environments. This changes the way we think about the origins of the conditions for life. It suggests that the chemical groundwork is laid very early, not after a planet has formed and cooled and developed oceans, but during the formation process itself, baked into the dust and gas from which the planet will be made. The carbon is there, the water is there, the complex molecules are there, all swirling together in a disk of gas around a star that is itself only a few million years old. And Webb can see it all, quietly, patiently, reading the chemistry of creation in the faint infrared glow of dust grains no larger than grains of smoke. From the collision of galaxies to the birth of planets, from shock waves spanning hundreds of thousands of light years to water vapor in a disk smaller than our own solar system, the telescope moves between scales with the same steady clarity. It does not rush. It does not need to. The light it gathers has already traveled for years, for centuries, for millennia, to reach that gold mirror. A few more moments of patience changes nothing. And so it watches the galaxies tearing each other apart and building new stars from the wreckage, the young suns wrapped in their cocoons of dust and possibility, the water and carbon quietly waiting in the warm inner regions of disks where no planet yet exists, but where one day, perhaps, a world will turn. All of it unfolding in infrared, all of it invisible to the unaided eye, all of it real. And beyond those warm inner regions, farther out from the young stars, in the coldest, darkest places between them, Webb found something else. Not light, not heat, but ice. In the deep molecular clouds where no starlight reaches, where temperatures fall to just a few degrees above absolute zero, there are vast stretches of darkness that even infrared struggles to penetrate. And within that darkness, clinging to dust grains smaller than a wisp of smoke, Webb detected thin coatings of frozen molecules. Water ice, carbon dioxide ice, ammonia, methanol, each one leaving its own faint signature in the infrared spectrum as background starlight passed through the cloud and reached the telescope's instruments. These are not dramatic discoveries. They do not shine. They do not explode. They are quiet, almost impossibly quiet. Just thin films of frost on particles so small you could never hold one between your fingers. And yet, these icy grains are among the most important things in the universe. Because they are the raw materials, the actual physical substance from which comets are eventually built. And comets, tumbling through young solar systems, carry that ice and those molecules with them, delivering water and carbon compounds to the surfaces of newly formed planets. The water in a comet was once ice on a dust grain in a dark cloud. The water on a planet was once carried there by that comet. And so the chain stretches back from oceans and rivers and rain, all the way to a frozen molecule clinging to a speck of dust in a cloud so cold and so dark that nothing inside it glows. Webb sees this. It reads the chemistry of that ice, identifies each molecule by the precise way it absorbs light, and in doing so, it traces the very first steps in a process that ends, millions or billions of years later, with a world that has seas. Not every world, not even most, but some. And it all begins here, in the cold, in the dark, in silence. There is a patience to this kind of science, a willingness to look at the smallest, faintest things and understand that they matter. That a thin layer of frozen methanol on a grain of dust is not trivial. It is foundational. Webb does not overlook these things. It was built, in part, to find them. And so it turns its mirror toward the darkness between stars, and it listens to what the ice has to say. Now, between the stars and the planets, between the massive and the small, there exists a category of object that belongs fully to neither. They are called brown dwarfs. Too massive to be planets, some of them dozens of times the mass of Jupiter, but not quite massive enough to sustain the hydrogen fusion that defines a true star. They are something in between, something that defies the neat categories we like to draw. They glow faintly in infrared, warm from the slow release of heat left over from their formation, but they do not burn. They do not shine in visible light. They simply drift, cooling gradually over billions of years, like embers that were never quite given enough fuel to become a fire. And Webb has studied them closely, carefully. What it found was unexpected. Some brown dwarf atmospheres show banded cloud structures, layers of different gases and particles arranged in horizontal bands, patterns that resemble the familiar stripes of Jupiter, but stretched across an object far larger and far warmer. Weather on a failed star. Winds and currents and layers of cloud, not made of water vapor as on Earth, not ammonia ice as on Jupiter, but something stranger. Webb detected the chemical signature of silicate sand clouds in the atmosphere of one brown dwarf, tiny grains of silicate, essentially sand, suspended high in a hot atmosphere, forming clouds that drift and shift and perhaps rain downward into deeper, hotter layers below. Sand clouds. It is a kind of weather never confirmed before Webb. Not rain as we know it, not snow, but a slow, hot precipitation of mineral dust falling through an atmosphere hundreds of degrees warm on an object drifting alone through interstellar space with no star to orbit, no system to call home. There is something quietly remarkable about this, that weather exists in such places, that the physics of atmospheres and clouds and wind applies not only to planets in tidy orbits, but to solitary objects glowing faintly in the dark between stars. Webb reveals this because it sees in infrared because it can read the spectral fingerprints of silicates and water and methane in atmospheres too cool and too dim for any visible light telescope to study in detail. And each brown dwarf it observes adds to a growing understanding of how atmospheres behave across a wide range of conditions, from the familiar to the deeply alien. These are not places anyone will ever visit. They're too far, too hot in some layers, too cold in others, too strange. But they are real, and they have weather. And Webb can watch it change. And then there are the questions that stretch back not just millions of years, but nearly to the beginning itself. In the earliest era of the universe, after the first atoms formed and the cosmic background light was released, there came a long period of darkness, hundreds of millions of years during which no stars shone, no galaxies had yet assembled, and the universe was filled with a fog of neutral hydrogen gas that absorbed any light that tried to pass through it. This era is sometimes called the Cosmic Dark Ages. And it ended, slowly, unevenly, as the first stars and the first small galaxies began to form, and their ultraviolet light started to ionize the hydrogen around them, stripping electrons from atoms, clearing the fog, making the universe transparent to light once more. This process is called cosmic reionization, and it is one of the great transitions in the history of everything. For years, astronomers debated what drove it. Was it the rare, brilliant galaxies, the brightest and most massive early objects that produced enough ultraviolet radiation to ionize the vast seas of hydrogen between them? Or was it something else? Webb has begun to answer this. And the answer, it seems, is quieter than expected. The telescope's observations suggest that it was not the rare bright galaxies that did most of the work. It was the small ones, the faint ones, the countless dim galaxies too small and too distant for previous telescopes to detect, each one producing only a modest amount of ionizing light, but together, in their enormous numbers, slowly burning away the fog of neutral hydrogen that filled the young universe. Not a few great fires, but a million small candles, each one contributing its share of light to a transformation that took hundreds of millions of years to complete. Webb sees these small galaxies now, or rather, it sees their light, which has been traveling for over 13 billion years. And in their spectra, it reads the evidence of ionizing radiation escaping into the space around them, doing the quiet, cumulative work of making the universe visible. It is not a dramatic story. There is no single moment when the fog lifted, no sharp boundary between dark and light, just a slow, gradual clearing, like mist burning off a valley as the morning warms. And Webb watches this from a million miles away, reading ancient light, and slowly, carefully, rewriting what we thought we knew about how the universe woke up. And there is another way Webb reads this ancient story. Not just by looking at the galaxies themselves, but by looking through them, past them, towards something even more distant. Quasars. These are the brilliantly luminous cores of very distant galaxies, powered by supermassive black holes consuming enormous amounts of matter. They shine so intensely that their light crosses billions of light years and still reaches us. And along the way, that light passes through the intergalactic gas that fills the space between galaxies. Webb studies the spectra of these quasars carefully, and what it finds in that light is a record of everything the light passed through on its journey. When neutral hydrogen is present in the intergalactic medium, it absorbs specific wavelengths of light, leaving gaps, dark lines, in the quasar spectrum. The more neutral hydrogen the light passed through, the deeper and broader those gaps become. By comparing quasars at different distances, and therefore different epochs, Webb can map how the intergalactic gas changed over time, how it transitioned from opaque to transparent, from a fog of neutral atoms to the clear, ionized medium that fills the universe today. It is like reading the history of a window becoming clean, not by watching it happen, but by measuring how much light passed through it at different moments in the past. And what Webb finds confirms the picture. The universe grew gradually more transparent over hundreds of millions of years, the fog thinning slowly, unevenly, in patches, as the light from those countless small galaxies did its quiet work. The universe, in a sense, learned to see itself. But Webb does not only look outward into deep time, it also looks at what that deep time left behind. When massive stars end their lives, they do not simply go dark, they explode in events so violent that for a brief time, a single star can outshine an entire galaxy of 100 billion suns. These are supernovae, and in their final moments, they forge and scatter the heavy elements that stars spent their entire lives building. Iron, silicon, argon, oxygen, sulfur. Elements that did not exist in the early universe, which contained almost nothing heavier than hydrogen and helium. Elements that had to be made, slowly, inside stellar cores over millions of years, and then released into space in a single catastrophic moment. Webb has observed the remnants of these explosions in nearby galaxies, the expanding shells of gas and dust left behind after the star is gone, and it has mapped the distribution of these heavy elements within those remnants with a precision that was not possible before. In the infrared, Webb can see through the dust that obscures these remnants in visible light. It can measure the temperature and density of different regions, identify specific chemical signatures, and trace how the ejected material is spreading and mixing with the surrounding interstellar medium. What emerges is a detailed portrait of how galaxies are chemically enriched over time, how each generation of stars leaves behind the raw materials for the next. And there is something worth sitting with quietly here. The iron in a supernova remnant Webb observes tonight is the same element that moves through living blood. The silicon scattered by an ancient explosion is the same element found in the crust of the Earth. The oxygen forged in a stellar core billions of years ago is the same oxygen that fills a sleeping breath. These are not metaphors. They are the literal history of the atoms in a human body, traced back through supernovae, through stellar cores, through the slow chemical evolution of galaxies across billions of years. Webb does not just observe this history from a distance. In a quiet sense, it is part of it, built from the same elements it studies, a mirror made of gold and beryllium, both forged in the hearts of stars long dead. And then, closer to home, much closer, Webb has turned its instruments toward our own solar system, the neighborhood we have studied for centuries, and even here, it has found things that were not expected. Jupiter, the largest planet in our solar system, has been observed by Webb in infrared light with a clarity and detail that ground-based telescopes cannot match. The images reveal the planet's banded cloud structure, its faint rings, and its auroras, glowing arcs of light at the poles where charged particles stream down along magnetic field lines. In infrared, the auroras appear in wavelengths invisible to the human eye, and Webb captures them with a sensitivity that reveals their structure and intensity in ways that complement what other observatories have seen. The planet's atmosphere, with its swirling storms and chemical layers, becomes a subject of spectroscopic study. Webb can identify the gases present at different altitudes, trace temperature gradients, and watch how the atmosphere changes over time. Even a world we have known for centuries still holds detail we had not fully seen. And then there is Enceladus, a small moon of Saturn, roughly 500 kilometers across, covered in a shell of bright white ice. It would be easy to overlook, a pale dot in the outer solar system, far from the warmth of the sun. But Enceladus is not quiet. Previous missions had detected plumes of water vapor erupting from cracks near its south pole, evidence of a liquid ocean beneath the ice, kept warm by tidal forces as Saturn's gravity flexes the moon's interior. Webb observed Enceladus, and what it measured was larger than anyone had anticipated. The water vapor plume extends thousands of kilometers into space, far beyond what earlier measurements had suggested. Webb traced it spreading outward, diffusing into the space around the moon, and feeding a faint torus of water molecules that encircles Saturn along Enceladus's orbital path. The plume is not a small leak. It is a continuous, substantial outpouring. Enceladus is actively releasing material from its interior ocean into space at a rate Webb can now begin to quantify. And within that plume, Webb's instruments search for chemical signatures, the presence of organic molecules, the composition of the water, the traces of whatever chemistry is occurring in the ocean below the ice. The ocean of Enceladus has never been visited. No probe has descended through the ice. No instrument has touched its water directly. But the ocean sends its contents upward, through the cracks, into space. And Webb reads what it can from the light that passes through that rising vapor. A hidden ocean, announcing itself. Quietly, persistently, sending its molecules out into the dark, where a gold mirror a billion kilometers away is listening. There is a thread running through all of this. From the faint galaxies that slowly cleared the early universe, to the quasar light that carries the record of that clearing, to the supernova remnants that scattered the elements of living things across the galaxy, to the storms of Jupiter and the hidden ocean of a small icy moon. Webb moves between scales that the mind can barely hold at once, from the edge of the observable universe to the moons of our own solar system, from the first few 100 million years of cosmic time to the present moment. And in each place it looks, it finds more than was expected. Not because the universe was hiding things, but because we had not yet had the eyes to see them. Beyond the planets, beyond the familiar architecture of our solar system, the outer reaches grow quiet and cold. Out past Neptune, in the dim borderlands where sunlight arrives as little more than a faint glow, there are worlds made of ice and ancient rock, objects that have drifted in slow orbits for billions of years, largely unchanged since the solar system was young. Webb turned its gaze toward some of these Kuiper Belt objects and found, on their frozen surfaces, carbon dioxide ice and organic compounds, molecules built from carbon and hydrogen and oxygen, the same basic alphabet from which living chemistry is written. These are not signs of life. They are something quieter than that. They are ingredients, preserved in the cold, waiting in the dark, as they have been waiting since before the Earth existed. The solar system, it turns out, is not empty between its planets. It is laced with chemistry, scattered across billions of kilometers of frozen silence. And then, closer in, Webb witnessed something more immediate. In late 2022, a spacecraft called DART deliberately struck an asteroid named Didymos, a small, tumbling rock in the inner solar system. The impact was intentional, a test of whether humanity could alter the path of an asteroid if one were ever found heading toward Earth. Webb watched what happened next. After the collision, a cloud of debris expanded outward from the impact site, dust and fragments and ejected material spreading slowly into space. Webb's instruments read the light passing through that cloud and began to identify what it was made of. The composition of the ejecta, the way different materials scattered and dispersed, all of it recorded in the spectrum of light that reached the telescope's mirror. This is one of the quieter miracles of what Webb does. It does not need to touch a thing to know it. Light carries information, and Webb is extraordinarily patient at reading it. When light passes through a gas, or reflects off a surface, or emerges from a warm object, it arrives carrying a kind of record, certain wavelengths absorbed, others brightened, each pattern corresponding to specific molecules, specific temperatures, specific densities, specific motions. Webb's spectrograph spread that light into its component wavelengths the way a prism spreads sunlight into color. And in those spread out patterns, scientists can read the chemical composition of an object, its temperature, how dense it is, and whether it is moving toward or away from us, and how fast. All of this from light alone. No sample returned, no probe dispatched, no instrument lowered into the thing being studied. Just light and the patience to read it carefully. This is how Webb examined the debris of Didymos. This is how it read the molecules in the atmosphere of a planet 40 light-years away. This is how it identified frozen water on dust grains in a dark molecular cloud. This is how it traced the heavy elements scattered by an exploding star. The same technique applied across distances that range from a few 100 million kilometers to the far edge of the observable universe. And it is at that far edge where the technique becomes something almost philosophical. When a galaxy is moving away from us, the light it emits is stretched. The wavelengths grow longer as the light travels across expanding space, and by the time it arrives at Webb's mirror, those wavelengths have shifted toward the red end of the spectrum and beyond, into the infrared. The amount of that shift, the redshift, tells astronomers how fast the galaxy is receding. And because the universe has been expanding at a measurable rate, the recession speed tells them how far away the galaxy is, and therefore how long ago the light was emitted. A galaxy with a redshift of 1 is seen as it was roughly 8 billion years ago. A galaxy with a redshift of 6 is seen as it was when the universe was less than 1 billion years old. Webb has measured redshifts above 13. At a redshift of 13, the light reaching the mirror left its source when the universe was less than 2% of its current age, roughly 300 to 400 million years after the beginning. The universe today is about 13.8 billion years old. Webb is seeing light that traveled for more than 13 billion years to arrive. And what it finds at those distances are galaxies, already formed, already containing stars, already, in some cases, containing the heavy elements that only form inside stars that have already lived and died. This is what unsettled the models. The expectation was that the early universe would be populated by small, irregular, primitive structures. The first tentative gatherings of matter, slowly assembling under gravity. It would take time, the models said, for galaxies to grow massive in structured time, for stars to form in large numbers, burn through their fuel, explode, and seed the next generation. But Webb found galaxies that appeared too large, too organized, too chemically enriched for how young the universe was when their light was emitted. Not slightly larger than expected, significantly larger, in some cases by amounts that required the models to be reconsidered. The universe, it seems, assembled itself faster than we thought. Star formation in those first few 100 million years was more efficient, more vigorous, more productive than the simulations had predicted. Why that is, remains an open question. Some researchers have suggested that dark matter may have behaved differently in the early universe than current models assume. Others have proposed that the first stars were more massive and shorter-lived than expected, accelerating the cycle of stellar birth and death and chemical enrichment. The honest answer, for now, is that we do not fully know, and that is not a failure. That is the work continuing. There is a boundary, though, beyond which even Webb cannot see. About 380,000 years after the beginning, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was a hot, opaque plasma, and light could not travel freely through it. It scattered endlessly, going nowhere. When neutral atoms formed, the universe became transparent, and the light that had been trapped in that plasma was suddenly free to travel. That light is still traveling today. It has been stretched by 13.8 billion years of cosmic expansion into microwave radiation, and it arrives at our instruments from every direction in the sky. A faint, uniform glow called the cosmic microwave background. It is the oldest light in the universe, a record of the moment the cosmos first became clear. Webb cannot see through it. No telescope can. That wall of ancient light marks the edge of what is directly observable. But Webb can see what formed just after it. The first structures to emerge from the cooling, expanding gas. The first concentrations of matter that gravity slowly gathered into the seeds of galaxies. The first stars that ignited in the dark and began the long process of building everything that followed. Webb sees those structures not as they are now, but as they were then, preserved in the light that has been traveling toward us ever since. The universe has a beginning that we cannot see directly, and a present that surrounds us on all sides. And between those 2 points, Webb is slowly filling in the story. Not all at once, not with certainty at every step, but carefully, wavelength by wavelength, redshift by redshift, spectrum by spectrum. Reading the light, finding what was there. And what Webb has found has not simply added to what we knew. In some places, it has asked us to reconsider what we thought we understood. The models that astronomers built over decades, careful, mathematically precise models of how the universe grew from a smooth, nearly featureless gas into the intricate web of galaxies we see today. Those models made predictions, and Webb has been testing them. Some predictions held, others did not. The early galaxies, those found just a few 100 million years after the beginning, were not supposed to look the way they do. The models suggested that galaxies at that age would be small, irregular, still assembling themselves from scattered clumps of gas and dark matter, still in the early, uncertain stages of becoming. But Webb found galaxies that were already large, already structured, already containing heavy elements that could only have been forged inside earlier generations of stars that had already lived out their entire lives. That takes time, and there did not seem to be enough time. This is one of the quieter tensions running through Webb's early years of science. Not a crisis, not a contradiction, but a persistent and honest question. How did so much structure form so quickly? Some researchers have begun to look at dark matter. Dark matter is the invisible substance that makes up most of the mass in the universe. It does not emit light or absorb it. We have never detected it directly, but its gravitational influence shapes everything. It is the scaffolding on which galaxies are built, the framework that determines where matter collects and where it does not. The standard model of dark matter, called cold dark matter, predicts a certain pace of structure formation, a certain timeline for when galaxies of a given size should appear. Webb's early galaxies may be asking whether that timeline needs adjustment. Perhaps dark matter behaves slightly differently than the model assumes. Perhaps it clumps more readily in some conditions. Perhaps the first stars formed more efficiently than expected, seeding structure faster than the models allowed. No one knows yet, and that uncertainty is not a failure. It is the natural state of science at its frontier. Webb has not broken our understanding of the universe. It has shown us where the edges of that understanding are and pointed, quietly, toward what lies just beyond them. The revisions will come slowly, through more observations, more spectra, more careful measurements of redshift and mass and chemical composition. Webb will keep reading the light, and the models will keep being tested against what the light reveals. This is how understanding deepens, not in sudden leaps, but in the slow, patient accumulation of evidence. Each new piece of data either confirming what was thought or gently, persistently suggesting otherwise. Webb was designed for exactly this kind of work, and it was designed to do it for a long time. When the telescope launched, the original estimates placed its operational lifetime somewhere between 5 and 10 years. That window was set by fuel. Webb carries a limited supply of propellant used to maintain its position at the Lagrange point, to make small corrections to its orbit, to keep it precisely where it needs to be. But the launch went well, unusually well. The trajectory was accurate enough that far less fuel was consumed than the conservative estimates had assumed. The margins that engineers had built in, the careful buffers against imprecision, turned out not to be needed. And so the fuel that remains may be enough to keep Webb operating for 20 years, perhaps more. 20 years of observations, 20 years of spectra and images and measurements, 20 years of light arriving from the edges of the observable universe and being carefully recorded. That is a long time in science. Long enough for entirely new questions to emerge that no one has yet thought to ask. Long enough for the instruments to observe the same regions of sky across different epochs and watch for change. long enough for a generation of astronomers who were students when Webb launched to build entire careers around its data. But Webb will do all of this alone. There will be no repairs, no upgrades, no astronauts arriving with new instruments or replacement parts. Hubble, which orbits just a few hundred kilometers above Earth, was serviced 5 times by space shuttle crews. Its mirrors were corrected, its instruments replaced, its batteries and gyroscopes renewed. That servicing extended Hubble's life and transformed its capabilities. Webb orbits 1,000,000 miles away. No crewed spacecraft currently in existence can reach it. No mission is planned to try. Whatever Webb carries into space is what it will always have. Its mirrors, its instruments, its carefully cooled detectors. These are fixed now, unchangeable, committed to the work they were built to do. This gives Webb's mission a certain quality of finality, a quiet completeness. Everything that could be done was done on the ground. Over 25 years of design and testing and refinement, and then the telescope was folded into a rocket and sent away, and the work of building it was over. Now, only the work of listening remains. Every day, Webb gathers light, and every day, that light is sent home. The data travels from the telescope's high-gain antenna across 1,000,000 miles of empty space to receiving stations on Earth, arriving at a rate of about 28 megabits per second, a steady, patient stream of information flowing continuously from the dark. Each day produces roughly 57 gigabytes of science data. That is not a large number by the standards of modern computing, but it is dense with meaning. Every gigabyte contains spectra and images and measurements that represent hours of careful observation, light gathered from sources billions of light years away, encoded into numbers that astronomers will spend years interpreting. None of it is kept private. After a short period during which the teams who proposed each observation have time to work with their data, everything Webb records is archived and made publicly available. Any researcher anywhere in the world can access it. Any student, any institution, any scientist with a question, and the tools to look. This is one of the quieter aspects of what Webb represents, not just a telescope, but a shared resource, a commons of cosmic observation that belongs, in some sense, to everyone. The light that Webb collects tonight left its source long before any human being existed. It has been traveling through space for billions of years, carrying information about a universe that was young and strange and nothing like the one we inhabit now. And when it arrives, it is not locked away. It is preserved and shared and made available to anyone who wants to ask what it means. There is something restful in that thought. All that ancient light, carefully gathered, carefully kept, waiting for the questions that have not yet been asked, waiting for the minds that have not yet turned toward it. The telescope drifts in its slow orbit, 1,000,000 miles from home, its gold mirror tilted toward the dark, and the data flows, and the archive grows. And somewhere on Earth, in the quiet hours, someone is reading the light, finding what was there. To understand what Webb is actually doing out there, it helps to hold one small fact quietly in mind. The telescope is sensitive enough to detect the warmth of a bumblebee at the distance of the moon. Not a fire, not a city. A single, small creature, its body barely warmer than the air around it. And Webb, from nearly 400,000 kilometers away, could find it. That is not an exaggeration. It is a measure, a way of expressing what infrared sensitivity at this scale actually means. The instruments were built to find the faintest possible signals, the oldest possible light. And they were built that way because the universe does not announce itself. It whispers. And to hear a whisper across billions of light years, you need something very still and very patient and very precise. Webb is all three. The telescope did not arrive quickly. It took more than 25 years from the earliest serious proposals to the moment it left the ground. 25 years of design revisions, engineering failures, budget pressures, delays, and quiet persistence. More than 10,000 people contributed to it across 14 countries. The final cost was roughly $10 billion. Those numbers are large, but they are also, in a way, beside the point. What they represent is something harder to quantify, a sustained collective decision made over decades to build something that would not benefit any single nation or institution, something whose returns could not be predicted, something whose value would only become clear long after the people who designed it had moved on. That kind of patience is rare, and it produced something that required patience at every level, even in the smallest details. Each of the 18 mirror segments was polished to an accuracy of about 25 nanometers. To put that gently into scale, a single human hair is roughly 25,000 nanometers wide, so the surface of each mirror segment was shaped to a precision 1,000th the width of that hair. Not approximately, not close enough, exactly that smooth, that true, that carefully made. Beryllium was chosen for the segments because it holds its shape in the extreme cold of space. Gold was chosen for the coating because it reflects infrared light with extraordinary efficiency. Every material, every curve, every surface was chosen for a reason, and the reasons were always the same: to lose as little light as possible, to gather as much of the faint, ancient signal as could be gathered. When the telescope launched and the mirror unfolded in space, the segments were not yet aligned. They were 18 separate surfaces, each tilted slightly differently, each reflecting a slightly different version of the same star. The alignment process took several weeks. Engineers on the ground sent commands, tiny adjustments, measured in nanometers, moving each segment by amounts too small to see, too small almost to conceive, until all 18 surfaces became, in effect, a single continuous mirror, 6.5 meters across, acting as one coherent eye. There is something meditative about that image. 18 separate pieces, each imperfect on its own, slowly brought into agreement until together they could see what none of them could see alone. And what they see, what they have been seeing since the first images arrived in the summer of 2022, has been quietly, persistently, rewriting what we thought we knew. The early galaxies were not supposed to look the way they do. The models said the young universe should have been full of small, irregular, chaotic structures. Galaxies still assembling themselves, still finding their shape. But Webb looked back to within a few 100 million years at the beginning and found something different. Galaxies that were already large, already organized, already containing the heavy elements that only form after generations of stars have lived and died. One candidate, designated Jade's GSZ 13-DO, may have existed just 320 million years after the beginning, and it was not a wisp, not a faint smear of early light. It had structure, it had mass, it had already, somehow, become something. The models did not predict this. And that is not a failure of the models so much as a gift from the data, a signal that something in our understanding of how the universe builds itself is incomplete, that star formation in the early universe was faster, or more efficient, or shaped by processes we have not yet fully accounted for. The questions are not closed, they are opened. Webb turned its attention to worlds closer in scale to our own, and found things there that were also unexpected. When it observed the atmosphere of a planet called WASP 39b, it detected carbon dioxide directly, the first time that had ever been done for any world beyond our solar system. And then, in the same data, something else appeared: sulfur dioxide, a molecule that forms not from simple chemistry but from photochemical reactions, from starlight interacting with the atmosphere in real time. This meant Webb was not just reading what an atmosphere contains, it was reading what an atmosphere does. The chemistry was alive, in a sense, active, driven by the light of a distant star falling on gases hundreds of light years away. And in the stellar nurseries, in the pillars of creation, in the Carina Nebula, in the dense clouds where stars are being born right now, Webb's infrared vision passed through the dust that had always hidden those places from view, and found protostars only a few 100,000 years old, still wrapped in the gas they were drawing inward, still becoming. Stars in the act of forming, caught in a moment that lasts longer than all of human history, but is still, by cosmic measure, a beginning. Every one of these discoveries is an opening. That is perhaps the most honest thing to say about what Webb has done. It has not resolved the deep questions about how the universe assembled itself. It has made those questions sharper, more specific, more alive. Each answer arrives with a new layer of uncertainty beneath it, and that uncertainty is not a problem. It is the shape of genuine knowledge, the feeling of a mind pressing against something real. The telescope will continue. Its fuel, used more efficiently than expected during launch, may sustain it for 20 years or more. 20 years of questions. 20 years of light arriving from places and times we have never seen. And all of that light, every photon that Webb has ever collected, every spectrum, every image, every faint signal pulled from the dark, left its source before it arrived here. The light Webb gathers tonight did not leave its origin tonight. It left billions of years ago. It has been crossing space ever since, through the expansion of the universe, through the slow drift of galaxies, through the long silence between things. And only now, at this particular moment, does it reach the mirror? Webb is always looking into the past. It cannot see the present state of the objects it observes. It sees only what they were sending outward, long ago, before the Earth existed, before the sun had formed, before any of this was here to receive it. There is something very still in that thought. The light was already traveling, long before there was anyone to look for it. And now, in the quiet of deep space, a million miles from home, a gold mirror the size of a small house tilts toward the dark and gathers it, carefully, patiently, one ancient photon at a time. The universe is very old, and it is still, in some sense, arriving, and so it gathers, not urgently, not with any sense of hurry. The mirror simply waits, angled toward whatever corner of the sky the astronomers have chosen, and the light comes to it, as light always does, at the only speed it knows. What arrives is old, profoundly old. And what Webb has done with that ancient light, in just a few years of operation, is quietly, methodically begin to revise things we thought we understood. Some of those revisions have been gentle. Small corrections to existing models, refinements at the edges of what we knew. Others have been something more significant than that. When Webb turned its instruments toward the very early universe, toward the faint, red-shifted glow of the first galaxies, astronomers expected to find what the models had long predicted: small, irregular, chaotic structures, young galaxies in the process of assembling themselves, still gathering mass, still finding their shape. What they found instead was different. Galaxies that were already large, already structured, already, in some sense, mature, and yet existing only 300 or 400 million years after the beginning of everything. One of them, a candidate known as JADES GSZ13-0, may have been shining roughly 320 million years after the universe began. That is an almost incomprehensible earliness. The universe itself is about 13.8 billion years old. This galaxy was already forming stars when the universe was barely 2% of its current age. And it was not alone. Webb found others like it, a population of early galaxies, more massive and more organized than any model had prepared us for. Galaxies that should not, according to our best understanding of how structure grows from the faint ripples of the early universe, have had enough time to become what they were. The models were not wrong in spirit. Gravity does pull matter together. Stars do form. Galaxies do assemble. But the pace of it, the efficiency of star formation in those first hundreds of millions of years, appears to have been significantly faster than we had calculated. Some of these ancient galaxies already contained heavy elements, oxygen, among others. That detail carries its own quiet weight. Oxygen is not a primordial element. It is forged inside stars, in the nuclear furnaces of their cores, and released only when those stars die. For oxygen to be present in a galaxy 300 million years after the beginning, an entire earlier generation of stars must have already lived out their full lives before that galaxy even appears in Webb's images. Stars that were born, burned, and died before the galaxies we are looking at had fully formed. There is a depth to that which takes a moment to settle. The universe was working faster than we knew, and Webb is the first instrument sensitive enough and tuned to the right wavelength to show us that the revisions did not stop at the distant past. Closer to home, though still unimaginably far, Webb has been studying the atmospheres of planets orbiting other stars, worlds that, until recently, we could detect but not truly examine. We knew they existed. We could measure their size, their orbital period, the faint dimming of their star as they passed in front of it. But what they were made of, what surrounded them, what chemistry might be occurring in their skies, that was largely beyond our reach. Webb changed that. In 2022, it observed a planet called WASP 39b, a large, hot world orbiting very close to its star, far too warm for life as we understand it, but chemically rich and well-suited for study. As the planet passed in front of its star, Webb captured the starlight filtering through the planet's atmosphere, each molecule leaving its own faint fingerprint in the spectrum, absorbing specific wavelengths in specific ways. And for the first time, in any exoplanet atmosphere, Webb detected carbon dioxide directly. Not inferred, not estimated. Detected clearly in the data. Water vapor was there as well, sodium, potassium, and something unexpected, sulfur dioxide, a molecule produced not by the planet's composition alone, but by photochemical reactions, by the star's light actively driving chemistry in the atmosphere above the clouds. That distinction matters more than it might seem at first. Detecting what an atmosphere contains is one thing. Detecting that active processes are occurring within it, that light and chemistry are interacting in real time, is something else entirely. It means Webb is not just reading a list of ingredients, it is watching a kind of weather, a kind of ongoing transformation. The technique that makes this possible is called transmission spectroscopy. It works because the universe, at the level of individual molecules, is extraordinarily specific. Each molecule absorbs light at its own precise wavelengths, and no two molecules absorb in exactly the same way. The spectrum of a planet's atmosphere is, in a sense, a fingerprint, and Webb's instruments are sensitive enough to read it. Webb has since turned this capability towards smaller, rockier worlds, planets closer in size to Earth. The TRAPPIST-1 system, a group of 7 roughly Earth-sized planets orbiting a cool red star about 40 light-years away, has been among the targets. Early results for the innermost planet suggest it likely holds no significant atmosphere, but the others remain to be studied carefully over time. The goal, still distant, still uncertain, is to one day find the spectral fingerprint of an atmosphere that could support life, or perhaps already does. Webb has not found that yet, but it has shown that the question is now, at least in principle, answerable. There is a third kind of revision Webb has been quietly making, not about the distant past, and not about other worlds, but about the places where stars are born. The Carina Nebula, the pillars of creation, dense, towering columns of gas and dust that have long been known to harbor young stars, but whose interiors were largely hidden from visible light telescopes. Dust blocks visible light. It scatters it, absorbs it, turns what lies within into darkness. Infrared light passes through. When Webb looked at the pillars of creation, it saw through the dust. And inside those ancient columns, it found protostars, stars only a few 100,000 years old, still wrapped in the infalling gas that is feeding them, still in the process of becoming. Some of them have not yet begun stable hydrogen fusion. They are not yet, in the full sense, stars. They are the moment just before. In Webb's mid-infrared view, the dense pillars themselves become semi-transparent. The towering structures that look so solid in visible light appear instead as faint, ghostly silhouettes. And behind them, and within them, the hidden architecture of star formation becomes visible for the first time. Hundreds of previously unseen young stars in the Carina Nebula alone. Protoplanetary disks around some of them, with gaps and rings that suggest planets already forming within the dust. Water vapor detected in the inner regions of some of those disks, in the zones where rocky worlds might one day coalesce. The raw materials of planets. The raw materials of oceans, perhaps. Drifting in the warm inner regions of a disk around a star that is itself still young. All of this was always there. Webb did not create it. It simply looked in the right way, at the right wavelengths, with enough precision to finally see. And what it has seen, again and again, is that the universe is older in its processes than we realized. More efficient, more layered, more active in its quiet corners than our models had room for. Each image is not an answer so much as a deeper question. Each spectrum, not a conclusion, but an opening. The mirror gathers, the data arrives, and somewhere, in the careful work of analysis, another piece of what we thought we knew gently shifts. And the shifting continues. Not in any dramatic way, not with announcements or revisions published overnight, but quietly, steadily, in the way that understanding always moves, one careful measurement at a time. Consider what Webb found in the earliest light it could reach. Galaxies, not faint smudges at the edge of detection, but structured, massive galaxies, already formed, already complex, existing just 300 or 400 million years after the beginning of everything. That number sounds large, but set against the full age of the universe, roughly 13.8 billion years, it is a very small fraction, less than 3% of all the time that has passed. And yet, there they were, already assembled, already containing heavy elements like oxygen, which means that before those galaxies, there had been earlier stars that had already lived full lives, burned through their fuel, and died, seeding the surrounding gas with the products of their cores. All of this in what cosmologists consider the very early universe. One candidate, a galaxy designated Jades GS-Z13-DO, may date to roughly 320 million years after the beginning, making it among the most distant objects ever observed. Its light traveled for more than 13 billion years before arriving at Webb's mirror. And when that light was analyzed, it told a story that did not fit neatly into the models we had built. The models had predicted that early galaxies would be small, irregular, still assembling themselves from the raw chaos of the young universe. What Webb found instead were galaxies that looked, in some ways, like galaxies that should not yet exist. Too organized, too massive, too far along in their development for the time available. This does not mean the models are wrong in every respect. Science rarely works that way. But it does mean they are incomplete. That something about how stars formed in the early universe, how efficiently, how quickly, was not fully understood. Some researchers have suggested this may require a closer look at dark matter's role in structure formation. Dark matter, which cannot be seen directly, but whose gravitational influence shapes how galaxies grow, may have behaved differently in those early epochs, or may have been distributed in ways our simulations had not fully captured. These are open questions, held carefully, without certainty, by people who spend their lives with this data. And Webb keeps providing more of it. Roughly 57 gigabytes of science data every day, transmitted home through a high-gain antenna at about 28 megabits per second across 1 million miles of empty space. All of it archived. All of it eventually made available to anyone who wishes to look. The telescope does not keep its findings. It sends them home. Closer to home, though still unimaginably far, Webb turned its attention to other suns, to the planets that circle them. And here, too, it found things that had not been seen before. A planet called WASP 39b, a gas giant orbiting very close to its star, became the first world beyond our solar system in which carbon dioxide was directly detected in the atmosphere. Not inferred, not suggested by indirect evidence, detected, its signature written clearly in the spectrum of starlight that had passed through the planet's outer layers on its way to Webb's instruments. The same observations revealed water vapor, sodium, potassium, and sulfur dioxide, produced by photochemical reactions driven by the star's radiation. That last detail carries a particular weight. Photochemistry means active processes. It means the atmosphere is not simply sitting there. It is responding, changing, being shaped by energy from above. Webb was not just reading a list of ingredients. It was watching chemistry happen on a world 40 light years away. This technique, transmission spectroscopy, the analysis of starlight filtered through a planetary atmosphere during a transit, is one of Webb's most powerful tools. Different molecules absorb different wavelengths of light. Each one leaves a fingerprint, and Webb's instruments are sensitive enough to read those fingerprints even on smaller, rockier worlds. The TRAPPIST-1 system drew particular attention. 7 planets, all roughly Earth-sized, orbiting a cool red dwarf star about 40 light years from here. Some of them sit within the zone where liquid water could, in principle, exist on a surface. Early results from Webb suggest that the innermost planet, TRAPPIST-1b, likely has no significant atmosphere. Its thermal emission measurements point to a bare, airless surface. But the others remain to be studied. The work continues, observation by observation, transit by transit. There is no rush in this. The telescope is patient. The universe is patient. Webb also looked inward, toward our own solar system, with the same careful attention it gives to the distant past. Jupiter's atmosphere, its faint rings, its auroras glowing in infrared at the poles. Saturn's moon, Enceladus, where a plume of water vapor was found extending thousands of kilometers into space, far larger than previous measurements had suggested. Kuiper Belt objects beyond Neptune, their surfaces carrying carbon dioxide ice and traces of organic compounds. Even an asteroid, Didymos, was observed in the aftermath of a deliberate impact, a mission designed to test whether a spacecraft could alter the path of a small body. Webb watched the debris cloud expand and helped characterize what had been thrown into space. The telescope does not distinguish between the ancient and the nearby. It simply looks, with the same quiet precision, at whatever is asked of it. Over 25 years in development, more than 10,000 people across 14 countries, a cost of roughly $10 billion. Each of the 18 mirror segments polished to an accuracy of about 25 nanometers, 1,000th the width of a human hair. And after launch, after the long unfolding in the cold of space, those segments were aligned over several weeks of adjustments so fine they were measured in nanometers. All of this so that the mirror could hold its shape, so that the light, arriving after billions of years of travel, would fall correctly. Webb cannot be repaired. It orbits too far away for any crewed mission to reach it. What was built on the ground is what exists in space, and it will remain there, gathering light for as long as its systems hold. The original estimate was 5 to 10 years of operation, but the launch was efficient, the fuel was conserved, and current projections suggest the telescope may continue working for 20 years or more. 20 years of questions. 20 years of light arriving from the past, being caught, being read, being slowly understood. Light Webb collects tonight, in this very moment, left its source long before the Earth existed. Some of it has been traveling since the universe was young, since the first structures were still assembling themselves from hydrogen and helium and the faint seeds of what would become everything. Webb does not see the present. It cannot. By the time any light reaches a detector, it is already history. The telescope is always looking backward, into the deep past of stars, of galaxies, of the universe itself. And yet something about that feels less like a limitation and more like a kind of grace. To look up and see not what is, but what was. To hold in a single image the light of a galaxy that no longer exists in the form it wore when that light departed. To know that the universe has been quietly at work for all this time, building and burning and scattering and beginning again. The mirror gathers. 1,000,000 miles from home, in the permanent cold of deep space, turned always away from the sun. 18 gold-coated segments, each one polished to a smoothness the eye could never perceive. Waiting, collecting, light older than the Earth itself, falling softly onto a surface the size of a small house. And somewhere in the long quiet between the stars, more light, still traveling, still on its way.